This week in class, we are discussing the types of research in political science. The purpose here is to familiarize you with terms, not to make you experts on each type. We will spend the next 2 months of class discussing all of these methods in more detail. But this video discusses the distinction between observational and experimental research, while the next discusses 2 types of observational research, qualitative and quantitative. The key distinction between observational and experimental research is in how you gather information. Observational research relies on information that already exists. It might be economic data, it might be opinions about healthcare reform, it might be images or texts, but it is already out there. In these cases, if you want to show that one thing causes another, you need to eliminate alternate explanations, or maybe show the process by which a cause leads to an effect. Everything that I talked about in my video on cause and effect. By contrast, experimental research creates data, and does so in a specific way. By controlling and randomizing who is exposed to a cause, an independent variable, or what we're going to call a treatment here, experimental researchers are better able to show causal relationships. In this video lecture, I'm going to explain how experiments work in political science in order to clarify this distinction. Then I'm going to end with a discussion of the pros and cons of observational versus experimental research. Okay, so for the next few minutes, I'm going to describe a lot of technical terms, but please bear with me. It will make more sense when I get into the example. So one thing that I did not mention in my video on cause and effect is the idea of inference, in particular, causal inference. This is just a technical term to describe what we do when we look for causal relationships. The challenge with observational research is that we're supposed to be observing what's going on in the world. But you can't observe everything, and sometimes we have to infer conclusions from the information we have. There are many types of inference, but here I will just explain the difference between descriptive and causal inference. Descriptive inference is making assessments about facts that are hard to observe. For example, what is Biden's approval rating? Or how many non-citizens vote? Causal inference is drawing conclusions about the causes of those facts. For example, does education influence a vote for Biden? Or do voter ID laws depress turnout? But there is a fundamental problem with causal inference, and yes, it is always referred to that way. The problem is that in order to determine causality in an ideal world, you would find 2 identical cases where one was exposed to a cause and the other was not. But those 2 identical cases don't exist. No 2 people are exactly alike, no 2 moments in time. And you can't expose the same person to a cause, again, this is called receiving a treatment in the language of experiments, and not expose them to the cause or the treatment at the same time. This makes more sense with an example. Let's say you wanted to see whether a vaccine works against the current strain of flu. To test this, you'd compare whether someone who got the vaccine is healthier than someone who didn't get the vaccine. But you can't both give and not give the same person a vaccine, so it becomes hard to rule out alternate explanations. You can't necessarily say that some other factor about the person who got the vaccine isn't causing their health outcome. So this is the fundamental problem of causal inference. You can never observe the effect of receiving 2 values of an independent variable on the same case at the same time. Observational research is always subject to this problem, but experiments can actually resolve it by looking at average treatment effects. Instead of comparing the effect of a vaccine on 2 people, we test it on a large number of people. What's important is that when you give out the vaccine, you give it to a randomly selected subset of your study population. If your group is big enough and you are truly random in your selection of people who get the vaccine, then all the differences between people that might affect the outcome get averaged out. On average, those 2 groups are going to be equivalent on any key factor, like gender, race, income, prior health status, or any characteristic that might impact the result, even those you can't think of. 2 people can't be the same, but 2 groups can be, at least on average. When the only difference between 2 groups then is the exposure to the treatment, here the vaccine, and we see a difference in outcomes, like getting the flu or not, then we can conclude that the vaccine worked, that it was a cause of better health. Let's look at a political example to see how this works in more detail. Back in the early 2000s, a scholar ran an experiment on whether negative campaign ads influence whether people turn out to vote. One way to study this would be to ask people in a survey whether they considered advertising when they decided whether or not to vote. But it's hard to know whether they would tell the truth or not. So the scholar got a list of all the voters in a certain area and divided that group at random into two smaller groups. He sent one of those groups a negative campaign ad about a mayoral election. Then he looked at voter records after the election to see who voted and who didn't. Since he randomly divided the group of voters into two groups, all of the demographic characteristics that could influence turnout, what we might call observable variables, and all of the things you can't observe, like personal preferences, should be randomly distributed between the two groups. The math doesn't work out perfectly when you look at 7 observations, but you would conduct this study with several hundred people. The more people you have in your study, the more likely you are to get equivalent groups. Then, to see what the effect of sending a negative ad was, you average the turnout of people who got the ad and subtract it from the average turnout of people who didn't. We'll talk more about how to design an experiment later in the class, but for now I just want to clarify 2 points. The first is random sampling versus random assignment. Random sampling is how you choose a representative group to study. You look at the whole U.S. population, or all the voters, and you choose a smaller group from that population that you can actually give a survey to. Random assignment is how you divide up that sample. You might flip a coin and assign some of the people in your sample to the treatment. They get the political ad or the vaccine, and some people to a control group that doesn't get the ad or the vaccine. For an experiment to work, you need both random sampling and random assignment. For observational research, you only need random sampling, assuming, of course, that that is the right case selection strategy for your question. The other big point of confusion is the difference between a control variable and an experimental control. An experimental control is a group of cases or observations. These are the ones that did not get exposed to the treatment, the independent variable. In this setup about plant growth, the control is the plant that did not get exposed to sunlight. Control variables are potential alternate explanations of the outcome you are studying. So in this case, they are the other things that might impact how a plant grows, like the soil, the amount of water, the type of plant, etc. In any experiment, your control group needs to hold all the control variables constant. They should have the same soil, amount of water, etc., so that the only difference between the control and treatment groups is the independent variable. Similarly, in our political advertising setup, the control variables are demographics like gender, race, and employment status. But the control group are the people who got the negative ad. Here, subjects 2, 5, and 6. With a large enough sample, your control variables should average out to be equal for both the control and the treatment groups. So those are the basics behind how experiments work. So why do we use them? Basically, they are great at establishing internal validity, even though they are weak in other areas. An experiment is the gold standard for establishing causality. You can be fairly certain that you have in fact shown a cause leads to an effect, but you only discover a cause for the group of cases you study. Just because you randomized within a sample doesn't mean that this sample actually represents the group you wanted to study. In our negative advertising example, for ethical reasons, this study was conducted around a non-competitive mayoral election, because basically it would be wrong to do something that could change the results of a competitive race just for research. So we have to consider whether this experiment actually tells us anything about the role advertising plays in other situations, here in competitive elections. Similarly, experiments don't explain how a cause leads to an effect. The diabetes drug Ozempic went through a series of clinical trials, these are medical experiments, to demonstrate it's safe and effective, but scientists haven't figured out yet how it actually reduces cravings and promotes weight loss. We know that it works, but we don't know why. The last set of disadvantages of experiments relate to the fact that you can't always do one. Not everything you want to know about politics can or should be tested with an experiment. So again, with these disadvantages, why do we do experiments? Basically, because showing causal relationships, establishing internal validity, is so hard. It's great when we can conduct a study that does that well. And frankly, most observational research tries to mimic this experimental setup. When we use control variables in statistics, or try to make sure two cases we study are similar in as many ways as possible, what we're doing is setting up a control and treatment group to study. The concepts are the same, even if we implement them in different ways.